Alrighty, howdy folks. I'm going to look at, come on, section 3.9. Start the slideshow. Yep. 3.9 is about related rates. Okay, and what we're going to do here is we are interested in the rate of change of some quantity. So it's called related rate. Basically, a rate, at least in our context here, is uh, the change with respect to time. For example, if a quantity is area and we call it A, then dA dt represents the change in that quantity A, the rate at which A is changing, dA dt, the derivative of A with respect to t. Excuse me. Typically, that t represents time. Okay. All right. Would, for instance, you'll pretty soon bump into this when you take physics. Suppose you're walking along a straight path. Obviously, as you're walking, your position is changing. You are at one place, the next moment you are at a different place, right? At a different position and all that. And if we say, how fast is your position changing? That's a valid question to ask, right? How fast is your position changing? Well, mathematically, what it is if you denote the position as x, then the instantaneous rate of change of position is given by dx dt, and that's what we call as speed. When you get into physics, you will learn that there is speed is the scalar quantity, and there is an equivalent thing, sort of equal thing, which is called velocity. But velocity is actually a vector quantity. That means you need to specify the magnitude and also the direction. Okay. Anyway, we are not going to worry about all the vector quantities and all that. Simply, all the point I'm trying to make is if there is a quantity x, then dx dt represents the rate at which that quantity is changing. Cool. My intention is not to solve way too many problems, simple, maybe one problem or two problems, and that's all I want to focus on. Let's look at a problem. If A is the area of a circle with radius r and the circle expands as time passes, find a dA dt in terms of dr dt. What's that? We have a circle and its radius is r, and the radius is changing. When the radius changes, automatically the area changes, right? And the question is, if you know dr dt, that means the rate at which the radius is changing, how fast is the area changing? At what rate is the area changing is the question. And then there's a specific problem with specific numbers in this one. Suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing when the radius is 30 meter? Right? Take a good look at that problem statement. We will be able to solve problems of this kind. Okay? How? The solution is like this. Always identify both the quantities and also the rates of change of any quantities, right? The quantities and rates of change of quantities. What are the quantities involved here? A is a quantity, area, and radius of the circle, r, is another quantity, and the rates of change are dA dt and dr dt, right? Okay, those are the quantities. And when you want to find this rate of change dA dt, this is what you need to do. Can you find a relationship between those quantities? Do you know some way area of a circle A is related to the radius r? Yeah, we have a formula. A equals pi r square. That's one of the first things that you need to do. Come up with an expression relating these quantities. And once you get that, you differentiate both sides with respect to t. Okay, once you find a relationship, you differentiate, take the derivative on both sides with respect to t. Okay, can you do that? Can you take the derivative of um, a with respect to t? What would you get? Well, that's just dA dt, a prime, or we'll call it dA dt. Now, on the other hand, d dt of pi r square is just a little bit more involved than dA dt. Would you agree? Pi is a constant, so the pi comes out. So pi times d dt of r square. D dt of r square would be a chain rule. So ddr of r square times dr dt. That means you'll get pi times 2r dr dt. There's a pi times 2r dr dt, which is what is 2 pi r dr dt. Right? I applied chain rule. Can you do something like this? So, by the way, there we go. They wanted us to find dA dt in terms of dr dt, and we did do that, right? Now, the part B, is it related to this? Suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing when the radius is 30 meter? For that, you have to interpret the numbers in terms of the quantities and variables. Okay. Um, what do we say? What do we make of that? If the radius of the oil spill increases at a constant rate of 1 meter per second, what do you think has been given to us? Right? Radius of oil spill increases at a rate of 1 meter per second. Any ideas? Yeah, is increasing at a rate. So the moment they say rate, then they are giving us dt, d some quantity dt. In this case, because it is radius and radius is represented as r, dr dt has been given to be 1 meter per second. Cool. So dr dt is 1 meter per second. Next, what else? How fast is the area of the spill increasing? How fast is the area increasing? What do we make of that? Would you agree? All we are being asked to find is dA dt equals what? So I put a question mark there. dA dt is what? And when the radius is 30 meter, so that means when the radius is 30 meter, when the R value is 30 meter, what is dA dt given that dr dt is 1 meter per second? Well, any idea why they had to give R? Yeah, they had to because notice dA dt is 2 pi r dr dt. So the rate of change of area depends on R and also dr dt. So both the quantities. That's why they had to give us R and dr dt. Cool? And the next thing that we need to do is just plug and chug. dA dt equals 2 pi r dr dt. Plug the values 2 pi times 30 meter and dr dt is 1 meter per second. Um, it used to be that I never used to write the units like that. But then when I saw that people in physics, they make sure to write units, I saw the value of it. I think it's a good idea to go ahead and keep writing the units. Um, so we have 2 pi times 30 is 60 pi. 60 pi times 1 is 60 pi. But the units would be a meter times meter per second makes it meter square per second. So we have 60 pi meter square per second. Cool. That's all there is to it. So there are some very interesting problems that you can solve in this one. but I'm not going to go over many of them. Should I? Yeah, I had a whole bunch of big one prepared for you, but yeah, I'm not going to do that. I'll just do one more problem. I may or may not ask you something like this even in a test. I just want to make sure that you at least get exposed to the concept. Okay. All right. A particle moving along a hyperbola xy equals 8. A particle is moving along a hyperbola xy equals 8. As it reaches the point 4,2, the y coordinate is decreasing at a rate of 3 centimeter per second. How fast is the x coordinate of the point changing at that instant? Okay. Now, one of the first steps that you need to do is you need to identify the quantities involved in the problem. And you may be given directly what those quantities are, or they may be stating it as a rate of change of some quantity. All right. So look at this one. A particle is moving along a hyperbola. What are the quantities involved? The quantities are x and y, right? And mostly they are saying how fast is the x coordinate of the point changing at that instant. They gave us how fast the y coordinate is decreasing. That means they gave us dy dt, and they're asking us to find dx dt, right? And like I said, um, well, you need to draw initial general and particular. So, um, oh boy, $100. Well, in this case, I'm telling you, this is much simpler. Um, you just have xy equals 8, right? And that's the relationship between x and y. You take the derivative on both sides. You can, yeah, here I wrote x equals 8 over y. ddt of x is equal to ddt of 8 over y. And that means dx dt, which is what we want, is going to be negative 8 over y squared dy dt, right? Would you agree the derivative of 8 over y is negative 8 over y squared? Where do I get times dy dt? Where do I get that? The derivative ddx of 1 over x is negative 1 over x squared, right? That's one of those things that I wanted you to memorize. So this is going to be dx dt equals negative 8 over y squared dy dt. Now, we have x equals 4 and y equals 2, and the dy dt is negative 3 centimeter per second. Dy dt is negative 3 centimeter per second. Why is that? Because it says the y coordinate is decreasing at a rate of 3 centimeter per second. And a quantity is decreasing, we assign a negative sign to it. Okay, if it's increasing, a positive sign to it. As simple as that. So dy dt is negative 3 centimeter per second. Now it's just a matter of plug and chug. Cool. So dx dt is negative 8 over 2 squared. So that turns out to be 6 centimeter per second. So as this particle is moving along this hyperbola, okay, the moment it reaches the point 4,2, its x coordinate is increasing. The y coordinate is decreasing at some rate because the y coordinate is decreasing because it's coming down, which means in the negative direction of y, right? Positive y direction points up. So if it is coming down, the direction is negative, and that's what makes it decreasing. Y coordinate is decreasing. Cool. If you understood this, awesome. If you did not, don't worry too much about it. I'm not going to test you with any complicated ones. All right. Where do we go? Done with this guy. Let's move on to the next part. 3.10. All right. The 3.10 part is about differentials. Okay. The way I covered it, we already used differentials when we talked about U substitution. In fact, I'm supposed to first cover this and then go to U substitution, because the U substitution, like if you plug in U equals x squared, for instance, du equals 2x dx, you say, that du is a differential. So I'm supposed to have covered all of that first, but this is the order I like. So let's see. Here is the idea. If we have a graph of y equals f of x, and there are 2 points, one point here and another point there, then let's say this point's x coordinate is a, and the other point is actually as an x distance of delta x from this a, then that would be a plus delta x, right? And this point, because its x coordinate is a, and it lies on the graph of y equals f of x, its y coordinate would be f of a. Are you okay with that? This point lies on the graph of y equals f of x. So if its x coordinate is a, the y coordinate should be f of a. If its x coordinate is 5, then the y coordinate would be f of 5. That's the idea. Cool. Uh, then, would you agree, by a similar argument, the y coordinate of this point should be f of a plus delta x? Yeah, because its x coordinate is a plus delta x, so its y coordinate should be f of a plus delta x. Okay, next. If the x distance between these 2 points is delta x, what should this y distance be called? Stands to reason, we should call it delta y, right? Change in y. So we'll call it delta y. But then there's something we can do. We can, oh, by the way, delta x and dx are exactly the same. Does that mean delta y and dy are the same? Answer is no. Okay. What is dy then? Dy is something that you get by doing something like this. You draw a tangent to this curve at a. Okay. At a f of a, that point, you draw a tangent to the curve. And along the tangent line, you measure the change in y. Not the exact change, not the actual change, but along the tangent dy. So that is dy, the differential dy. Cool. Delta y is the actual change, dy is the change along the tangent line, or the differential. It's called a differential. Are dy and delta y the same? Clearly not, right? As you can see. But the thing is, I have exaggerated the dimensions quite a bit here. If we make delta x to be very small, then you will hardly notice a difference between dy and delta y. So the whole point is to keep delta x or dx very small, so that the difference between delta y and dy is negligible. They are approximately equal. So that's the concept of differentials. When delta x is small, then delta y is approximately equal to dy. But we know that dy dx in this context, because it came from the tangent drawn at a. A tangent is nothing but f prime of a. Tangent drawn at a, the slope of the tangent is nothing but f prime of a. And that's what our dy dx is. Now, if you multiply both sides by dx, then dy is f prime of a dx. Right? Hey, can you multiply by dx like that? Yeah, you can. As you can see, dx is just a quantity, the change along the x from as you go from one point to the other. So dy is f prime of a dx. Cool. Now, f of a plus delta x, that is nothing but f of a, this y value, plus delta y. Would you agree with that? In order to find this height f of a plus delta x, I should go from the x-axis up to f of a, and add this additional distance, which is delta y, as you can see here. So f of a plus delta x is f of a plus delta y. But then we'll say delta y is approximately equal to dy, but dy is f prime of a dx. So we can say this quantity is approximately equal to f of a plus f prime of a dx. That is the key to the whole thing. All right, f of a plus delta x is approximately equal to f of a plus f prime of a dx. You must kind of memorize that one. Okay. Now, we are going to solve quite a few problems using this concept of differentials. Use a linear approximation to estimate the given number 1.999 to the 4. Okay. The way you do this is, we'll use this equation that we just got, and step 1 would be to identify what f of x is, right? It must have sounded weird that the question is about what is the approximate value of 1.999 to the 4, and I'm saying, yeah, let's use this f of a plus delta x is approximate. What is that f, man? What has that got to do with these numbers? That's why we must somehow look at the problem statement and say, what is our f of x in this case? All right. So here is my point. Because we are being asked for 1.999, the quantity raised to 4, we should say f of x is x to the 4. Cool. What if they were asking us for, say, square root of 4.01? Square root of some number. Oh, okay. So f of x would be square root of x in that case. What if they were asking us for, say, sine of uh, sine of 46 degrees? In that case, sine of x would be our f of x. Get the idea? So f of x in our case is x to the 4. Nobody tells you that. You have to figure out from the problem statement. Cool. The next thing is we need to identify what A is. Again, nobody will tell you. You have to figure this out. And here is the way you figure out A. Since we need f of x at x equals 1.999, we choose A that is close to this x, right? And we should be able to evaluate f of A fairly relatively easily. Is there a number that is close to 1.999 where we can find a to the 4 relatively easily? Yeah, would you agree? 2 would be such a value? Good. 2 is pretty close to 1.99 and 2 to the 4 is 16. So we can do that. So that's why we picked a to be 2. Right? Are you okay with this? I'll solve quite a few problems, a few more problems, so that you clearly understand this concept. So a equals 2. All right. So that means we can find f of a 2 to the 4. Good. What else? We need delta x. Step 3. How do we find delta x? Here is the idea. As soon as you find a, you will say a plus delta x is equal to whatever this number that you need to figure out a for. We needed to figure out f of x at x equals 1.999, right? We will call that 1.999 as a plus delta x. Okay, a plus delta x is this one. But a, we just said, is 2, and so 2 plus delta x is 1.99. Can you figure out delta x from that? Yeah, subtract a 2 from both sides, and you get negative 0.001. take a look at that really well. Because we need the function's value at 1.999, we will say that to be a plus delta x, and based on that, based on the a, figure out delta x. All right. So we know f of x, x to the 4. We know a, 2, according to this form, and we just figured out delta x. So the only thing that's left for us is to figure out f prime of a. Um, so first we need to find f prime of x, and then we can find f prime of a, right? That's the way to find f prime of a. Pay attention to what I'm about to say. You should never do something like this. You cannot say, I'll find f prime of a by differentiating f of a. Wrong. What is that? F prime of a is not the derivative of f of a. Instead, f prime of a is f prime of x evaluated at a. That's a key distinction. Why is that? If you figure out f of a, that turns out to be a number, right? And if you differentiate a number, you get 0. And every time that's what's going to happen, regardless of what that function is. You evaluate a function at a point, some a, and you get a number, and you differentiate it, you keep getting 0 all the time. So f prime of a is actually f prime of x evaluated at a. Cool. So keep that in mind, please. F of a we know is this. F prime of x is 4x cubed. And so f prime of a would be f prime of x evaluated at 2, and that turns out to be 32. Cool. Looks like we have all our quantities. And so find f of a plus delta x. We have 1.999 to the 4. That's what we need to find. That's exactly equal to f of a plus delta x. Is that true? Is 1.99 to the 4 equal to f of a plus delta x? Yes. On what grounds can I say that? Check this out. Is a plus delta x equal to 1.999? Yes. And x to the 4, 1.999 to the 4, isn't our f of x equal to x to the 4? Yeah. So f of a plus delta x, that is equal to f of 1.999, is 1.999 to the 4. So that's what I wrote here. And that we know is approximately equal to f of a plus f prime of a delta x. And so I'm just plugging and checking. F of a is 16, we found. F prime of a is 32. Delta x is negative 0.001. And turns out to be 15.968. Cool. Now, you might be wondering, come on, what's the big deal about this? The big deal about this is the kind of concept that will become very useful in solving differential equations and things like that in a numerical way. All these things come in very, very handy at a later time. All right. So this is an interesting concept. By the way, if you actually punched into a calculator as to what 1.999 to the 4 is, that gives, at least in my calculator, I found that to be 15.968023992. And what we got is 15.968. Can you live with that? Yeah, that's mighty close, right? So 5 significant digits, the two values are agreeing. So this is not a bad idea at all. Cool. Next, use a linear approximation to estimate the given number, square root of 100.5. Cool. Solution. What's the first step? No, we'll of course use this equation. Step 1, identify f of x. I'll let you tell me. Right? Yep, you got it. So f of x should be square root of x. Because we need square root of 100.5, we'll say f of x is square root of x. And then we need to identify a. What is a? A should be found by picking a number. We need square root of 100.5. That means at x equals 100.5, we want a value. So is there a number that is close to 100.5 where we can figure out square root of 100, square root of that number very easily? Yeah, obviously 100, right? Excuse me. We can find f. So a is 100. All right. The next thing, find delta x. How do you find delta x? You let a plus delta x equals this number where you need to evaluate 100.5. So the actual x value where f of x is needed is 100.5. So a plus delta x is 100.5. A, we chose that to be 100. And so we get delta x to be positive 0.5. Cool. And then we need to find f of a, f prime of x, and f prime of a. F of a, f of a is f of 100. F of 100 is square root of 100. So that's 10. And f prime of x, the derivative of square root of x is 1 over 2 square root of x. So f prime of a is 1 over 2 times square root of 100, which is 1 over 20. Cool. Find f of a plus delta x, and that is square root of 100.5 is f of a plus delta x. I just plugged in numbers. And this turns out to be 10.025. And the calculator says 10.02496883. If you round this to 4 at this decimal place, the fourth decimal place, that actually does become 10.0250. So we are right. So this is pretty good. Cool. Are you getting the hang of this? All right. I think this is the last one. Cosine of 29 degrees. We'll use that equation. F of x. You know it, right? F of x is cosine x. Yep. Identify a. Do you know cosine of some value that's pretty close to 29 degrees? Cosine of 30 degrees. Cosine of 30 degrees is square root of 3 over 2. So we'll pick a to be 30 degrees and find delta x. How do you do that? You say a plus delta x is equal to 30 degrees, right? Is 29 degrees and a is 30 degrees. So delta x is negative 1 degree. And so that's the thing is, for the delta x, you need to convert it into radian. You cannot leave it in degrees. When you multiply, you have to convert into radian. That's the only slight difficulty in this one, okay, as opposed to the other problems. 1 degree is, to convert degrees to radian, you need to multiply by pi over 180. So that's what I did. I took negative 1 degree and multiplied that by pi over 180 to convert it into radian. Okay, so delta x is this. Now, as before, let's find f of a, f prime of x, and f prime of a. F of a is f of 30 degrees, cosine of 30 degrees, like I said, is square root of 3 over 2. F prime of x. What's f prime of x? Negative sine x, right? And f prime of a would be negative sine of 30 degrees, and that's negative 1/2. Sine 30, sine pi sixths is negative 1/2. And sorry, sine pi 6 is positive 1/2. We have a negative sine pi 6, so negative 1/2. And as before, now plug f of a is square root of 3 over 2 plus f prime is negative 1/2 times delta x is negative pi over 180, and you got this. If you leave it like that, full credit. Okay, I'm not expecting you to figure out what pi over 360 is without a calculator. All right, folks. This is it. So if you can solve these kinds of problems, I'll be a happy man. Alrighty.